lecture we discuss the branching algorithm for cell formation considering cells that are based on products. After discussing the branching algorithm, we will discuss the case with multiple products, and then we will move on to discuss models that consider operator allocation and assignment. Now, in the earlier lecture we saw a model for unidirectional flow. We saw the integer programming model which had 78 variables and 84 constraints. We also mentioned that this problem can become very large if the number of operations are large. Now, instead of solving it by integer programming, now can we look at a branching algorithm which can give us an optimum solution to this problem, perhaps considering or taking less time than the integer programming formulation. So, we will see one such branching algorithm. We will use the same matrix where there are 6 operations that have to be performed. There are 6 candidate machines and we want a solution that ensures unidirectional flow. Now, let us look at a solution that ensures unidirectional flow considering exactly 3 machines m equal to 3. The earlier integer programming formulation actually gave us a solution with 2 machines, but it did not have any restriction on the cycle time. Here what we try and do is we try to choose 3 machines, we ensure unidirectional flow, and we also want to find out the minimum cycle time with such an assignment. So, those are the conditions or the constraints or parameters of the problem. Since there are 3 machines that we will choose, the branching algorithm will have 3 levels, each level corresponding to a machine, and in each level we allocate operations to the position or to the level. So, what we will do in the branching algorithm is we would begin with 4 nodes. So, we will begin with 4 nodes. So, we will start here, we will begin with 4 nodes which we call node 1, node 2, node 3 and node 4. Now, node 1 we will assign operation number 1 here. Here we will assign 1 and 2, here we will assign 1, 2 and 3, and here we will assign 1, 2, 3 and 4. Now, since there are 3 machines and 6 operations have to be assigned, now these will represent the set of operations that are assigned at level 1, which means we can do 1 or we can do 1 and 2 or we can do 1, 2 and 3 or we can do 1, 2, 3 and 4 on the first machine. It is like there are 3 machines here, we stop with 1, 2, 3, 4 here because it is like assigning 1, 2, 3, 4, but the remaining 5 and 6 will have to go to these 2 machines. So, if we build another node here with 1, 2, 3, 4, 5, then this one cannot get any operation assigned to it because 6 will automatically go to this. So, we would not possibly, we do not want to put a 5th node here, the 5th node will come much later. Now, every time we do this, we should look at, is there a feasible machine that can handle this? If there is no feasible machine that can handle this, then the node will become infeasible. For example, let us go back and do that calculation. Now, we have assigned operation 1 here. So, there are several machines that can do operation 1. So, we are okay with that. Now, we have assigned operations 1 and 2 here, we still have one machine which can do operations 1 and 2, which is M4. So, this can give us a cycle time of 7, because we have M4 that can do 1 and 2, the time required is 7. So, this is okay. Now, we have still only one case of a machine that can do 1, 2 and 3, which is again M4, and the cycle time is 9 here. And we have only one case of a machine which can do 1, 2, 3 and 4 with cycle time equal to 12. Now, if we assign only operation 1 to the first position, then we could use machines 1 or 3 or 4 or 6, and the minimum cycle time possible is 2. Now, in addition, if we assign 1, 2, 3 and 4 to position 1, which is like writing 1, 2, 3, 4 here, so automatically M4 has to go here. Now, 5 will have to go to this position and 6 will have to go to this position. Operation 5 will have to come here, operation 6 will have to come here, because we are having 3 machines and we have a restriction that every machine should have at least one operation and unidirectional flow has to be maintained. So, for this straight away 5 will have to come here and 6 will have to come here. Now, 5 can be done on machines 2, 3 and 6. Right now this is on M4, so we still have feasible machines 2, 3 and 6 we can do. 6 can be done on 1, 2, 3, 5, 6, we are again okay. So, if we look at this, there will be a cycle time of 12 on this, because this will be M4. Now, to do operation 5 we could consider M2 or M6, both have cycle time of 1. So, we could consider 1 and either M2 or M6, and for operation number 6 we could consider 1, 3, 5 and 6. So, we could consider M5 with minimum cycle time of 3, so M5. So, we have one feasible solution with cycle time equal to 12. So, we write here 1, 2, 3, 4 feasible solution cycle time equal to 12, M4, M2, M5, operations 1, 2, 3, 4, 5, 6 with cycle time equal to 12. So, this has been done. So, now we go to this, and now we can branch off here further with here operation 1 is given. So, at this level I can have operation 2, which would mean at the third level I will have 3, 4, 5, 6. I could have 2, 3, I could have 2, 3 and I could have 2, 3, 4 and I could have 2, 3, 4, 5. So, these are all the possibilities. Now, this would ensure that 6 will come to the third stage. So, now I go back, the moment I have written this, there are only 3 stages. So, this would simply mean that, so this is node number 5, node number 6, node number 7 and node number 8. So, the moment I assign 1 and 2, I have to do 3, 4, 5, 6 to the third. So, because there are only 3, so right here the third one gets fixed automatically. This would mean a solution where operation 1 goes to the first position, operation 2 goes to the second position, which means 3, 4, 5, 6 will have to go to the third position. So, this would give me another solution with 3, 4, 5, 6 going to the third position. Now, I look at this table and I realize that there is no single machine that can do 3, 4, 5 and 6. Therefore, this solution is infeasible. Not at this stage, but at the next stage, because next stage would mean 3, 4, 5, 6 go here. Now, I look at 1, 2 and 3, which means at the third stage I will have 4, 5, 6. Now, I go back and see 4, 5, 6 would force me to use M3 here or M6. So, this can be M3 or M6. Since I am trying to minimize cycle times, I try to use M6 here at the third stage with cycle time equal to 2 plus 1 3 plus 5 8, whereas if I had used M3 my cycle time would have been 10. Now, I go back to 2 and 3, 2 and 3 I can use M2, M4 and M5. I choose M5 with minimum cycle time equal to 3, and then I go to 1, I can use 1, 3, 4 and 6. I have already used 6. So, I have 1, 3 and 4. So, I use M1 here. So, the solution will be again feasible solution with cycle time equal to 8, with M1 coming here with 2. So, M1, M5, M6 with 1, 2, 3, 4, 5, 6. So, I update the solution from a best solution of 12 to a best solution of 8. Now, I go back to this 1, 2, 3, 4 would force 5 and 6 here. Now, I go back for 5 and 6 I can use M2 or M3 or M6. So, I use M2 with cycle time equal to 4. So, I do M2 with cycle time equal to 4. Then I go to 2, 3, 4, and from this table I realize that machines 4 and 5 can carry out 2, 3 and 4. Machine 4 has a cycle time of 4 plus 2 plus 3 9, while machine 5 has a cycle time of 2 plus 1 3 plus 5 8. So, I would choose M5 here to do this is equal to 8, and then I have 1 here. So, now I have, so operation 1 can be carried out in 1, 3, 4 and 6. I can use any of them 1, 3, 4 and 6. So, I would use M1 there. So, again feasible solution with cycle time equal to 8. I choose M1 in the first stage, M5 in the second stage and M2 in the third stage. So, I would assign 1, 2, 3, 4, 5 and 6. Again I have a solution with cycle time equal to 8. So, it does not get better. So, I can either update to this solution or I can leave with this solution. Both of them have cycle time equal to 8. If we are going to have other considerations, then we could choose one of them depending on other considerations like cost, for example. Right now we are not considering cost of machines in this algorithm. So, the solution is the same up to this point, the solution is the same whether we take this or we take this. Both give us a cycle time of 8 and use 3 machines. Now, we go back to this one where 1, 2, 3, 4, 5, which means automatically 6 has to come to this one. So, now I go back 6 I can do it on 1, 2, 3, 5 and 6, but I realize somewhere right here when I have to do 2, 3, 4, 5 on a single machine I realize that I do not have a machine that can do 2, 3, 4 and 5 on the same machine. Therefore, this becomes infeasible. This becomes infeasible. Now, I already have a solution with cycle time equal to 8. Now, if I branch from this node, I have already allocated 1, 2 and 3 operations at the first stage, and I have got this 9 from the table which says M4 is the only machine that can do operations 1, 2 and 3 with minimum cycle time or only cycle time equal to 9. So, if we proceed from here and if we assign the remaining operations 4, 5 and 6 to 2 different machines, the cycle time can still be 9 or more. It cannot become less than 9, because I already have in this stage the minimum possible cycle time as 9. So, proceeding from this particular node cannot give us a solution with cycle time 7. We already have feasible solutions with cycle time 8. Now, the moment we have feasible solutions with cycle time 8, we would now like to explore whether the cycle time can actually reduce further. Now, this already has a minimum cycle time of 9, and proceeding from here cannot reduce the cycle time further. Therefore, we fathom this node by considering that this 9 is greater than 8. So, this 9 represents a kind of a lower bound is greater than upper bound. It is a minimization problem. Every feasible solution is an upper bound. So, when this lower bound is greater than upper bound, we fathom. Now, the only node that remains here is 1 and 2, from which we have to branch. So, let me just write this 1 and 2 separately and branch from there, so that it does not get very congested here. So, we would write, this is node number 2 that I have here, and node number 2 has operations 1 and 2 given here with a minimum cycle time of 7. Now, this 1 and 2 with minimum cycle time of 7 came by using M4. M4 is the only machine which can do 1 and 2 together and give us a cycle time of 7. Now, from here we have to branch to the next stage, where I assign machine operation 3 here. So, I call this node number 9, with operation 3 here, and I assign node number 10 with 3, 4 and assign node number 11. So, this will have 3, 4 and this will have 3, 4, 5. Now, we look at each one of this. Now, this I put 1, 2, 3. So, the third machine should have 4, 5 and 6. Now, I go back to this table and I realize that M3 is the only one that M3 and M6 can do 4, 5 and 6. So, M3 takes time equal to 10, M6 takes time equal to 8. So, I choose M6 with cycle time equal to 8, and I can actually stop here, because I do not have to go back and allocate a machine here and a machine here, because I already have cycle time equal to 8 here. So, when I do the machine allocation and compute the 3 individual cycle times and choose the maximum of the 3, that can only be 8 or more. So, the lower bound here is 8, and I already have feasible solutions with 8. And using the same principle that lower bound is greater than or equal to upper bound, I fathom this node, because if I proceed I can only get a solution with 8 or more. So, now I look at node 10, this is going to put operations 5 and 6 on the third machine. I go back to this table and I realize that operations 5 and 6 can be carried out on M2, M3 and M6. At present I choose M2, so I choose M2 with cycle time equal to 4. M2 with cycle time equal to 4. Now I go back to operations 3 and 4. Operations 3 and 4 can be done by M4 and M5. Now already M4 and M5. So I go back, I assign M4 has a cycle time of 5, M5 has a cycle time of 6, but I tentatively assign M4 with minimum cycle time of 5, but then I go back to 1 and 2 and I realize M4 is the only one that I can do with 1 and 2. So therefore this 7 is going to absorb M4. So this 7 is going to absorb M4 here. This would force me not to use M4 here, but to use M5 here, and M5 for operations 3 and 4 has a cycle time equal to 6, M4 has cycle time equal to 7. So this gives me another feasible solution. Another feasible solution with M4, M5 and M2, which will do operations 1, 2, 3, 4, 5, 6 with cycle time equal to 7. Now cycle time equal to 7 is smaller than cycle time equal to 8, so the solution gets updated. Now the moment the solution gets updated, I do not have to do this because this already has a cycle time of 7. So even if I proceed here and if I find a feasible solution, its cycle time cannot be less than 7, it can only be 7 or more. So here I do not proceed, I say lower bound greater than or equal to upper bound, because upper bound is 7 now, feasible solution is upper bound. So from here already I know it is 7, I cannot get something less than 7, so I stop. If I do not follow this logic of lower bound less than greater than equal to upper bound and fathoming the node, I will go back and see this is going to force me to use 6 here, and then I go back and find out, is there a machine that can do 3, 4 and 5 together? There is no such machine, so this would have been fathomed by infeasibility. After some computational effort and search, now right here I can fathom this. So there is no node, the best solution is the one that has cycle time equal to 7 with 3 machines M4, M5 and M2 with operations 1, 2, 3, 4 and 5, 6 done. So this algorithm is actually a branch and bound algorithm. Because we have used the idea that when the lower bound is greater than or equal to upper bound, I can fathom the node. So a node gets fathomed by infeasibility, by a feasible solution, and when lower bound is greater than or equal to upper bound, there is no more nodes available to proceed, the algorithm terminates. Now this branch and bound algorithm is very useful to solve this kind of a problem. We can have additional restrictions brought in like budget restrictions on the machines and so on, it can be done. The only place where we have to be a little careful is that at earlier places, when here we have only one machine, so we wrote 7, somewhere we could have alternatives, say at this stage. When we had alternatives, we chose the minimum cycle time as a lower bound, but we did not assign a machine there. We should not do that. Like what happened here, if we had assigned 4 M4 here, then we will not have anything else to do here, it might throw up an infeasibility, which is not correct. So only when we reach this stage, we have to go back and then we have to make sure that do we have enough machines which can provide a feasible solution. So this portion alone makes the branch and bound a little more involved with more search and so on. Very technically, if we look at this problem, this itself is a machine selection problem, which is a sub problem when we have alternate machines. So, the sub problem of machine selection, right now we used it heuristically by picking the minimum cycle time, because this problem instance is a small instance. For large problem instances, we should be solving a small knapsack problem inside, which will try and give us the best selection of machines. So, still we can use this branch and bound algorithm, provided we understand all these aspects of the branch and bound algorithm. So, the optimum solution, considering 3 positions and 3 machines and unidirectional flow, is given by this solution with 1, 2, 3, 4 and 5, 6 getting allocated with cycle time equal to 7. Now, the next model that we will see is when we have multiple products. So far we have seen that the cell makes only one product. Now, what happens when the cell makes more than one product? So, we choose or use these 2 matrices to represent multiple products. So, from this we can say that there are 2 products, each product has, first product has 6 operations, second product has 5 operations, the cycle times are given there. Now, we want to choose minimum number of machines such that we assign each of these operations to these machines, and we have a cycle time restriction on this. So, the formulation is a logical extension of one of the earlier formulations, where we had a restriction on the cycle time and we minimize the number of machines. We now have a second product that also comes in. So, xi equal to 1 if machine I is chosen, Yij equal to 1 if operation j on product 1 is assigned to machine I, Zij equal to 1 if operation j on product 2 is assigned to machine I. So, the objective function will try to minimize the number of machines considering the first product. Each operation of the first product should be assigned to only one machine for every j. Considering the first product, each operation is assigned to only one machine. Considering the second product, each operation is again assigned to only one machine. Now, for the first product, Pij Yij sigma is less than or equal to 6 times xi. If we take the first product and if we take, for example, the operations assigned to machine 3, then 3 y31 plus 3y34 plus 2y35 plus 5y36 should be less than or equal to 6 x3. Only when x3 is chosen the 6 units of time is available and whatever is assigned should be less than or equal to 6. In a similar manner, sigma q ij z ij is again less than or equal to 6 xi. We are not saying that put together the cycle time is 6, cycle time is 6 for each product. Both the products are not going to be produced at the same time in the cell. At the same time the cell is going to produce only one of the products, and whichever one it is making the cycle time should be less than or equal to 6. So, this will again ensure that if we take the second product and if we are looking at machine number 5, then we will have a constraint which is 2 y phi 2 plus 1 2 z phi 2 plus 1 z phi 3 plus 5 z phi 4 plus 3 z phi 5 is less than or equal to 6. So, this will again ensure that the same thing happens. Then we have xi, yij, zij equal to binary 0 1. So, this will be the formulation considering multiple products, minimizing the number of machines and subject to a cycle time restriction. So, if we finally look at the solution which has we also try to minimize the cost in this case. So, the objective is not to minimize sigma xi, but the objective is to minimize ci xi. The cost of the machines are given in the earlier as in the earlier model. So, we finally look at x1, x2 and x6. So, let us go back. So, x1, x2 and x6, x1, x2 and x6 will have a cost of 40 plus 35 75 plus 30 105. So, $105. So, we use machines 1, 2 and 6 are chosen. So, machines 1, 2 and 6 are chosen. Now, for the first product we have said that 1 and 6, 2, 3 and 5 and 4. So, 1 and 6, 2, 3 and 5 and 4, and for the second product 1 and 5, go to machine 2, operation 2 goes to machine 1, 3, 4 and 3, 4 goes here. So, the cycle times will be 1 and 6 would give us a cycle time of on machine 1 operations 1 and 6 will give a cycle time of 6, 2, 3 and 5 will give a cycle time of 5, 4 on machine number 6 would give a cycle time of 2 for the first product. So, all cycle times are within 6. Cycle times here for the second product, machine 1 operation 2 has a cycle time of 5, machine 2 operations 1 and 5 have cycle time of 6, machine 6 with 3 and 4 also have cycle time of 6. So, machines 1, 2 and 6 are chosen. So, this is product 1 and this is product 2. Now, the only thing in this solution is we have not considered unidirectional flow. So, we could consider unidirectional flow and build similar models. We have already seen a model with unidirectional flow. Now, we should look at another model for Z as well, including along with Y we should also have a z, then we will have additional constraints and solve this problem considering unidirectional flow in this. Similarly, we can also do a branching algorithm for multiple products the way we have demonstrated this. So, these are some of the models that we have seen which would look at product based cellular manufacturing. So, to sum it up, we have seen several models, all of these are shown here. To minimize number of machines, to create a cell that can carry out all the operations with cycle time restrictions, with cost restrictions, with unidirectional flow and considering multiple products. Several combinations of these can also lead to intermediate models, but all these can be solved optimally. We have right now shown some integer programming formulations for these, we have shown one branch and bound algorithm for these. We have not looked at heuristic solutions for these. Several heuristic solutions are also available which can be used to get solutions very quickly. Now we look at one more aspect of cellular manufacturing, which is called operator and task assignment. So let us go back to operator and task assignment. So far we have seen assigning machines to cells and parts to cells, assigning machines to cells created machine cells, assigning part to cells created part families. Now we are going to see how we assign operators to cells. Now that comes under the topic called operator and task assignment. So first thing that we do is what is called rabbit chasing. Now let us assume that there is a cell. Now most of these come for product based cells, they can also be extended to the regular cells. So let us say there is a cell that makes one product, there are 5 machines and the task times on these 5 machines are task time on these 5 machines are 12, 8, 10, 9 and 6. In fact, these need not be 5 operations whose times are 12, 8, 10, 9, 6. This can even be the outcome of any of these optimization problems or the branching algorithm, where multiple operations are carried out on a machine, but the total of the operation times are 12, 8, 10, 9 and 6. Now let us look at what happens when, now this is one kind of layout. Another kind of layout that we can think of is that is like this. So this is 12, this is 8, this is 10, this is 9 and this is 6. These are the 5 machines. Now what do we do by rabbit chasing? Now suppose we have only 2 operators and this first operator comes, takes a piece from here, does the first operation, then goes to the second, goes to the third, fourth, fifth and comes out. Meanwhile, second operator follows the first operator and continues. Now once the first operator is finished, this operator will leave this part here and then he or she will take another part and do this operation. So we will now trace the output of this cell when we have this happening. The first operator starts at time equal to 0 and finishes at time equal to 12, which is shown here. Then the operator moves to the second machine and finishes at 20, which is 12 plus 8, and then moves to the third machine, finishes at 30, 20 plus 10 is 30. Fourth machine finishes at 39, 30 plus 9 is 39, and then takes 6 time units to finish at 45. Meanwhile, the second operator would start the work. So, at time equal to 12, the first machine is free, the second operator is also free. So, the second operator starts work at time equal to 12, finishes at 24. But by 20, the second machine is free because the first operator has already moved. So, second operator starts at 24 and finishes at 32. So, again the machine number 3 is free at 30 itself. So, second operator starts at 32 and finishes at 42. Again machine number 4 is free at 39 itself. So, he starts at 42 and finishes at 51, and finally finishes at 57. So, for this calculation we need to take the time which is the maximum of these two and add the corresponding time of 9 to get this 51. So, the second operator finishes a piece at time equal to 57 and the second piece comes out at time equal to 57. Now, the first operator is once again available to come to M1 at time equal to 45. So, again starts at 45 and finishes at 57, by which time M2 is free and the whole process continues. So, operator 1 again finishes at time equal to 57, 65, 65 plus 10 75, 75 plus 9 84, and 84 plus 6 90, and the third piece comes out at time equal to 90. Operator 2 had finished at 57 and comes back to the starting point. Now, the machine number 1 is also free at time equal to 57. So, operator 1 starts at 57, finishes at 69, and from 69 finishes the second machine at 77, 87, 96 and 102. So, we observe that operator 1 has completed pieces at 45, 90, again 135 and so on, while operator 2 will complete pieces at 57, 102, 147 and so on. So, time between successive pieces will be 12 and 23 respectively, as we see from this table, and therefore, the average output or the average time taken is 12 plus 23 by 2, which is 45 by 2, which is 22.5. So, a simpler way of saying is the total is 45, there are 2 operators. So, on an average a piece will come out at time 45 by 2 equal to 22.5 time units. We now see the same computation, but with 3 operators. So, as I mentioned, the first 2 operators would finish at time equal to 45 and 57 respectively. Now, the third operator starts. The third operator can start at time equal to 24 because M1 is free at time equal to 24. So, the third operator starts at 24 and finishes the work at 36, by which time M2 is free. So, starts at 36 and finishes at 44. Once again M3 is free at 42. So, this person can start at 44, take 10 more time units, finish at 54, similarly finish here at 63 and finish the piece at time equal to 69. Now, operator 1 starts again at time equal to 45, operator 1 is free. So, operator 1 comes back, starts at time equal to 45 because this machine is free at 36. So, operator 1 can start at time equal to 45 and finishes at 57. Again this machine is free at 44, therefore, operator 1 starts at 57 and finishes at 65 and so on, finishes this at 75, 84 and 90. Now, operator 2 had finished the first piece at 57. Now, operator 1 has finished the second piece on M1 at 57. So, operator 2 can now start at 57. Of course, we assume walking times as negligible in all these computations, otherwise it will go up a little bit. At the moment, for illustration, we assume that walking times are negligible. So, the person starts at 57 and finishes at 69 here. So, again M2 is free at 65. So, operator 2 can start at 69 and finish at 77. Again M3 is free at 75. So, the person starts at 77 and finishes at 87. Similarly, finishes at 96 and again finishes at 102. Now, from this calculation we can understand that 3 pieces actually come out in every 45 minutes, because 45 and 01 is second piece comes out at 90, similarly 57, 102 and so on. So, 3 pieces will come out every 45 time units. The average time per piece is 45 by 3, which is 15 time units. The simpler way to say this is total is 45, there are 3 operators. So, the average time is 45 by 3, which is 15. Let me show the computation for 4 operators now. So, the first 3 operators will perform as shown in the previous slide, that is up to this 69. So, up to this 69 the 3 operators will perform. Now, let us look at the 4th operator. The 4th operator starts the first one at time equal to 36, finishes at 48, by which time M2 is free. So, 4th operator finishes at 56, by which time M3 is free, 4th operator finishes at 66, again M4 is free. So, 4th operator finishes at 66 plus 9, 75, by which time M5 is free. So, 4th operator starts at 75 and finishes at 81. Now, operator 1 comes back to the starting point. Now, operator 1 is free at 45, but the machine is free at 48 only. Therefore, operator 1 comes back for the second piece and can start only at 48, which is larger of this 48 and this 45, starts at 48 and ends at 60, by which time M2 is free. Therefore, this is over at 68. Again this is free at 66, therefore, this will be over at 68 plus 10, 78. Again this is free at 75, therefore, this will be over at 78 plus 9, 87. Again this is free at 81, therefore, this is 87 plus 6, which is 93. Now, operator 2 comes back to the starting point. Operator 2 is available at 57, but the machine is available only at 60. Therefore, operator 2 can start only at 60 and finish at 72. So, the completion times for operator 2 will be 72, 80, 90, 99 and 105. Now, we observe that 4 pieces come out for every 48 units, that is 45 and 93, the difference is 48 units. So, 4 pieces will come out at steady state every 48 units. The average time is 48 by 4, which is 12. If we go back and make this comparison, in the earlier examples of 2 operators, we said total is 45, there are 2 operators, so average is 22.5. Here total is 45, 3 operators, average is 15. But here total is 45, 4 operators, the average is not 45 by 4, but it is 48 by 4, which is 12. So, what has happened? What has happened in this case is, when we had 2 operators, the average is 22.5, which is more than the maximum of these 5 individual processing times 12. Therefore, the average stays at 22.5. Here the average is 15, which is more than this 12. But when we have 4 operators, the average is 11.25. If I take 45 by 4, it is 11.25, which is smaller than 12. Now, 12 is the maximum among the unit processing times and is called the bottleneck processing time. So, when the average total time by the number of operators, in this case 11.25, becomes smaller than 12, the bottleneck will start dominating and the output will only be every 12 time units. And that has happened because if we observe carefully, operator 1 is completes the work at 45, but can take up the work only at 48. So, there is that 3 time unit that gets carried. So, 45 plus 3 will become 48, and 48 divided by 4 will give us 12. So, when the number of operators is such that the total processing time divided by the number of operators becomes less than the bottleneck time, the output will only be that of the bottleneck time. For 3 operators, the total by number was 15, which is more than 12. So, the output was a piece every 15 time units. With 4 operators, it is 45 by 12, 45 by 4 is less than 12. So, 12 dominates. Now, at steady state, the output will be 12 time units for every piece. If we do this computation for 5 operators, again we can show that the output will be only 12 time units, which is the bottleneck time. Therefore, when we do this rabbit chasing, we should first find out the total and we should find out the number of operators. When the total by number of operators is more than the bottleneck time, the time per piece will be total processing time by number of operators. When total processing time by number of operators is less than the bottleneck, then the output will be the bottleneck. So, this is the first model that we have seen, which uses the idea of rabbit chasing and tells us how we compute the cycle time when operators follow each other. Subsequent models we will see in the next lecture.